Tensors are used in many applications to store and compute on data. Sparse tensor formats were developed to store tensors that contain many zeros, so that instead of storing every single coordinate and its value, instead, these formats only store the non-zeros, resulting in much more efficient storage and performance when computing with these tensors. For example, the tensor on the left can be stored as a tree. Each leaf represents a non-zero, and the interior nodes represent the ith, jth, and kth coordinates. The hierarchical nature of the tree imposes an ordering on the data. Iterating over the coordinates of this tree is done naturally in IJK order. My name is Susie Mueller, and today I will show that the ordering of the sparse tensor storage significantly affects the computation time of different tensor operations. I will also show how to change that index ordering through sparse tensor transposition. A sparse tensor transposition algorithm can be thought of as a radix sort with multiple passes, where each pass sorts a different mode of the tensor. Latter half of this video, I will describe an algorithm that uses the structure of certain transpositions to skip some of these passes. This approach can dramatically accelerate tensor transposition. But first, let's look at element-wise matrix multiplication to see how the storage order can asymptotically affect computation time. In element-wise matrix multiplication, we multiply together non-zeros with matching coordinates from two matrices and place the result in a third matrix. This requires a merge of the non-zero coordinates of the two input matrices. When the two matrices have matching index orderings, we simply iterate over both matrices and compare the coordinates. We can co-iterate over these two matrices in linear time. However, if we were to now change the index ordering of the second matrix to have the jth coordinate first, we can no longer co-iterate over both matrices in linear time. We must instead locate the matching elements in the second matrix for each non-zero in the first matrix. This requires a search at each level of the tree in the second matrix, or some type of additional mapping like a hash table to help locate the element. Element-wise computations with tensors that don't have matching index orders was listed as a benchmark operation by the Parallel Sparse Tensor Algorithm Benchmark Suite. And as we saw, it can be asymptotically slower to do than when the index order matches. A better strategy for these operations may be to transpose the second tensor to match the first tensor and then co-iterate in the natural order. This would be especially beneficial if we were doing many of these operations using the same tensor. Transposing a sparse tensor resorts the coordinates to be in a new index order. In the case of the coordinate sparse tensor format, transposing the tensor is exactly equivalent to resorting a list of numbers, where each coordinate represents a digit in the number. Using a radix sort, we start with the last coordinate in the index ordering and do a histogram sort on each coordinate until we reach the first coordinate in the index ordering. A histogram sort is a stable sort that is linear on the size of the dimension and the number of non-zeros. For example, to transpose this matrix from the permutation ij to the permutation ji, we first sort on I and then on j. However, if we look closer at this sort, we see that the first sort doesn't actually have any effect on the matrix. The matrix was already sorted on I. We can skip this step and do the sort even faster. This insight of skipping a sort is one of the things that allows the half-perm algorithm, which transposes sparse matrices, to be so fast. The idea of omitting passes can be extended to higher order tensors and take advantage of the partial sortedness of the tensor's coordinates. In this 4-tensor example, we can see how omitting passes can reduce the work needed to go from ijkl to jilk. Radix sort could do this in 4 passes, but we can do it in 2. If we look at this permutation, we can see that j is being moved above I and L is being moved above k. We can do each of these in a single pass. First, we want to move j to the top of the ordering. Doing a histogram sort with j as the key will do this. Now we want to take this tensor and move L above k. In order to maintain the ordering of the top modes, we can create buckets of equivalent ji coordinates and sort within each of these. This allowed us to do the entire transpose using only 2 passes. In our paper, we described linear time implementations for both histogram sort and bucketed histogram sort, so we treat each of these passes as approximately equal. The Quesadilla algorithm is able to find these sort schedules for any permutation of any order tensor and will minimize the number of passes needed to get to the desired output permutation. To see whether the schedules produced by the Quesadilla algorithm would work in practice, we implemented the passes as histogram sorts, and then tested the schedules by running them for all permutations of 12 different data analytics tensors from the Frost dataset. We compared Quesadilla to 3 types of sorts: quicksort, radix sort, and splat sort. Splat sort is a state-of-the-art hybrid radix and comparison-based sort. We found that Quesadilla was the best strategy in 60% of all permutations that were tested, and overall performed significantly better than radix sort, showing that omitting passes can be helpful in practice. In this graph, we plotted the percentage of permutations that ran under a given runtime to visualize how the sort strategies performed across different permutations. The x-axis here is the absolute runtime in milliseconds, and the y-axis is the percentage of permutations that were completed before that time for each sort strategy. For example, if we look at around 350 milliseconds, we can see that 50% of the trials for Quesadilla strategy have completed. For radix sort, the median runtime of permutations is closer to 600 milliseconds. The steep line for radix sort shows that all permutations were completed in roughly the same amount of time. Quesadilla, on the other hand, takes advantage of the opportunity to omit passes for certain permutations and is able to complete these permutations faster. If you want to read more about transposing sparse tensors and see proofs and more data from our experiments, they can be found in our full paper at arXiv. The code for both our serial and parallel implementations can also be found on GitHub. Thank you.